Well, the topic of this lecture is numerical integration. Previous week I sent you the link to the video file of lesson of previous year, this topic. That's why I just briefly repeat the main points from this topic, and we consider how we can implement the formulas of numerical integration in the program written in C++. Very briefly, where the problem of numerical integration may arise. Suppose that we want to make a sheet like this, where the cross sections has the form of sine. And the question is, what is the length of initial flat sheet? What flat sheet we should take to make a irrigated sheet 4 meters long? Suppose that the height of each wave is 10 centimeters, and suppose that each wave has a period approximately 2 pi. How we can find the length of initial sheet, flat sheet? From the mathematical analysis, we know a formula that the length is integral from 0 to 4, because the sheet of 4 meters long is needed, square root 1 plus f prime of x and square dx. F of x is sine, so f prime of x is cosine, and we have a integral from 0 to 4, 1 plus cosine x and square dx. Trigonometric functions are very simple functions. We always use it as examples. But in spite of its simplicity, we cannot find this integral by using ordinary methods. Nobody can find it, because there are no formula for computing the integral from this function. We can find only the numerical approximation. So, numerical integration is a process of producing a numerical value for the integration of a function over a closed set. The examples of such integrals are written here. And from mathematical analysis, we know a very simple formula that can give us exact answer. But this exact answer depends on so-called anti-differentiation. We should find the antiderivative of the function f of x. We should find such function f capital X, such that f prime x, f capital, equals to f of x. Then we can apply this very simple formula. but there are a lot of functions that do not have simple antiderivatives. If we know such a value, if we know the antiderivative, we can apply this formula and we can get the exact answer. Well, I can type the example in Microsoft Word using formulas. Suppose that we want to find the integral from, for example, from 0 to pi sinus x dx. How we can find it? What is antiderivative of sinus? Antiderivative of sinus is minus cosine. Oh, I'm sorry, it's just so the derivative of sine is cos, derivative from cos is minus sine. Yes, right. Minus cosine x is antiderivative of sinus. And to compute this integral, we should substitute. We should write a substitution. Let me find, yeah, like this. Minus cosine x and lower and upper bound. Lower bound is 0. Upper bound is pi. From 0 to pi with such substitution. It equals to the difference, the first minus, then cosine pi minus cosine 0. Then we can substitute here the exact values. Cos 0 is 1. Cosine pi is minus 1. Minus 1 minus 1 equals to minus 2. And minus minus 2, finally we have 2. As a result, the exact value of this integral. But this integration we can make only in just simple cases. When the function f of x is more or less complex, in this case we cannot find the antiderivative. In this case, we should suggest some formula how to compute this value approximately. How to find the approximate value of numerical integral. One of the ideas how to compute the integral numerically is to replace f of x by another function g of x that approximates f of x well and is easy integrated. If f of x approximately equals to g of x, it follows that integral from f of x dx approximately equals to integral of g of x dx. And very good candidates for the functions g of x are polynomials. Because polynomial, we can write an interpolating polynomial. We can interpolate any function using polynomial in a certain set of nodes, of course. And polynomial is very easy integrated function. If we take a polynomial f of x that approximately equals to g of x, suppose that f of x approximately equals to g of x, then we can say that integral of g of x will be approximately equals to f of x. And we know how to find the polynomial that approximates the function f of x. We can find Lagrange or Newton interpolating polynomial. And polynomials are very good functions for integration because x power n has very simple antiderivative. If g of x equals to x power n, what will be the antiderivative of g of x? In this case, g of x, g capital, will equal to x power n plus 1 over n plus 1. Very simple formula. After that, we can say that g prime of x, g capital, equals to g of x. Suppose that we want to evaluate the integral in the interval from a to b. Then we can select the nodes in this interval and find a Lagrange interpolating polynomial. This is a general form of Lagrange interpolating polynomial. And after that, we can say that integral from a to b f of x dx approximately equals to integral from a to b p n of x dx. But as far as the Lagrange interpolating polynomial can be written in this form, f of x here is a constant. Only auxiliary polynomials Li depends on x. So we can move the sign of the integral inside the sum. And we can write that integral from a to b Pn of x dx equals to sum from I equals to 0 to n f of xi integral from a to b ln of x dx. In this way, we obtain a formula that can be used for any function f of x. The general form of this formula is presented here. Approximation of the integral equals to sum of very simple coefficients ai times f of xi. So the value of the integral is nothing that the sum of the function values with some coefficients. Very simple formulas. Only we need to do is to find these coefficients. We should find the coefficients ai. We can find it only once. We can find the integral from a to b li of x dx. This formula is called a Newton-Cotes formula if the nodes are equally spaced. The simplest case of a Newton-Cotes formula is so-called trapezoid rule. What is a trapezoid rule? It's a formula that we obtain if we consider the interpolating polynomial of degree 1 and the nodes x0 equals to a and x1 equals to b. If we have two nodes, we can find a line that passes through these nodes, these points. This line is a graphical interpretation of linear polynomial, and their auxiliary polynomials L0 of x and L1 of x that we used to find this line is written here. B minus x over b minus a and x minus a over b minus a. If we find the integrals from a to b of L0 of x dx and the integral from a to b L1 of x dx, these two values will be equal. A0 equals to A1 and equals to 0.5 times b minus a. The corresponding formula will have the following form. Approximated value for the integral equals to b minus a over 2 times f of a plus f of b. This formula is called trapezoid rule because it has a very simple graphical interpretation. Suppose that this is an unknown function f of x. This is a point x0 equals to a. This is a point x1 equals to b. Using these 2 points, we can find a linear polynomial, a line that passes through these points. And this line will be graphical interpretation of a polynomial, Lagrange interpolating polynomial of degree 1, p1 of x. And if you remember, on the first lesson, we discussed about the geometric meaning of the integral. And the geometric meaning of the integral is the area under the curve between these 2 points. And if we consider the area under the curve of the function and the area under the curve of this linear function, you can find that these two values, these two areas, will be more or less the same, will be close. This is the difference between these two values. Moreover, the rear under the line will correspond to a rear of a trapezoid. This is the trapezoid, and the rear of trapezoid can be computed as f of a plus f of b times b minus a over 2. This formula corresponds to the rear of a trapezoid. But this value corresponds to only one interval from x0 to x1. If we need to compute a lot of such integral that can consist of a lot of intervals, we need to just summarize it. The integral from x0 to x1 plus the integral from x1 to x2 plus the integral from x2 to x3 and so on. I think you can find the value, you can easily find the trapezoid rule in Wikipedia. If you type trapezoid rule, the first link will to the Wikipedia, the same formula, and this picture illustrates how we can find the integral from this point to this. We can find it as a sum of the integrals between this point and this and this, this and this, and so on. The rear under the curve will be approximated as a sum of the areas of these small trapezoids. Before we consider the concrete implementation of the trapezoid rule in C++ program, let me say a few words about error analysis. As far as f of x can be represented as p1 pn of x plus error term, this is the formula of interpolation. The error of computing the integral of a function will be the difference between the real function value, the real value of the integral and the approximation. And this value will be the integral of this error term. And in the case of a trapezoid rule, when n equals to 1, x0 equals to a, x1 equals to b, we can directly compute this error term. Just substitute here the points x0 and x1 and compute the integral of a quadratic function. In this case, the final result will be the value that includes two terms. First term depends on h, where h is the difference between the points x0 and x1. It's a step, the distance between x1 and x0. And the second term is a second derivative, the value of the second derivative of a function at some point xi. This term has order 3. It means that if we decrease the distance between the points x1 and x0 10 times, the error becomes 1000 times smaller. But this error corresponds to only one interval between x0 and x1. If we consider the error on the interval from x1 and x2, the error from x2 and x3, the error term from x3 to x4, in this case, we should summarize all these errors. And finally, the error term will have the order 2, h power 2. Let's check it in a concrete example in Visual Studio. Suppose that we want to find the integral of a function x plus sinus x. First of all, let's find the real value of the integral. Real value of the integral will be useful because we want to compare the approximation that we get and the real value of the integral. How to find the real value of the integral? F of x, in our case, equals to x plus sinus x. What will be the antiderivative of f of x? Let me remind you that antiderivative means that f prime of x will capital F capital prime of x equals to f of x. In our case, situation is very simple because we have here one term a linear polynomial and the second term is a sinus trigonometric function, and we will have the value x squared over 2. This is antiderivative of x minus cosine x. It will be the antiderivative. Let's declare it in the form of a function. Double f double x and return x times x over 2 minus cosine x. It will be antiderivative. Suppose that we want to compute an integral from a to b. In this case, the real value of the integral will be here. I've put the final result, but I can find it using antiderivative. It will be f of b minus f of a. F of b minus f of a. Then let's declare a new variable for approximated value of the integral. Let's use n as a number of intervals. Let me remind you that the integral on the large interval can be computed as a sum of the smaller integrals step by step. This plus this plus this and so on. Let n be the number of such intervals. What will be the length between the points xi and xi minus 1? In our case, it will be 1 over n. But this one, what is this one? It's just b minus a over n, the length of initial interval over n. Let xi will be a, and now how to find the value of the integral? According to the trapezoid rule, what we should do? We should find the sum f of a, where a is the left point, plus f of b, where b is a right point. What is the left point? Left point is xi. So it will be f of xi plus, what will be the right point? Right is xi plus h. We compute this sum. And as far as the term h over 2, b minus a over 2 is included at every term, we can move it outside the sum and multiply the resultant value of approximation at h over 2 after the sum, after this loop. Okay. Well, that's all. We can run this program. Suppose that the number of intervals is 10. The real value of the integral equals to 0.9596 and so on. Approximation of this real value equals to 959. As you see, the difference is at the fourth sign after decimal point. That's why the error, the difference between real value and approximation, will be approximately 3 times 10 power minus 4. Let's remember it. 3 times 10 power minus 4. Then, suppose that I increase the number of the intervals. Let me increase it to 100. In this case, the difference between real value and approximation becomes 3 times 8, 3.8 times 10 power minus 6. The error decreased 100 times. This fact verifies the quadratic rate of convergence. We decrease the step 10 times, and the error is decreased 100 times. So if the number of intervals is 100, the error is approximately 10 power minus 6. What happens if I decrease the step 10 times more? So if I take the number of intervals 1000, let's do it. If I select the number of intervals as 1000, the error becomes 100 times smaller. It becomes 10 power minus 8. If I select 10,000, the error becomes 10 power minus 10. Quadratic rate of convergence. I can use any functions here. Let's change sine to cosine. For example, let me write here cos. What should I change? I should change antiderivative. Antiderivative of cos is sine. So I should change here cos to sine. Let's check. Let's select number of intervals equals to 10. Yeah, the values of the integral changed, but the order of the error is the same, 10 power minus 4. If I increase the number of steps, the quadratic rate of convergence will hold. Well, this is one of the simplest rules, so-called trapezoid rule. Let's come back to the presentation, and let's consider another more powerful, more complex rule called Simpson's rule. As you remember, the trapezoid rule becomes from this graphical interpretation. We take 2 points, A and B, and approximate the area under the curve with the area of a trapezoid. But let's select 3 points. If we have 3 points, we can build a Lagrange interpolating polynomial of degree 2, quadratic polynomial, parabola. And after that, we can find an integral of this quadratic polynomial. Quadratic polynomial includes three coefficients, L0, L1, and L2. These coefficients are written here. Well, I skip the integration of these coefficients, but it can be integrated, and after the integration, we can find that the integral from a to b L0 of x equals to the integral from a to b L2 of x dx, and the value of the integral equals to h over 3. So two coefficients are equals to h over 3. And one coefficient, the middle coefficient, equals to integral from a to b L1 of x dx for h over 3. And if we substitute all the values here, we find very simple but very powerful formula that called Simpson's rule, Simpson's formula. Integral from a to b f of x dx equals to h over 3 f of x0 plus 4 f of x1 plus f of x2. The power of this formula is consists in the following fact, because the error has order 5. It's a very powerful result. If we have h order h power 5, in this case, it's enough to decrease the step 10 times. And after that, the error will be decreased 100,000 times, h power 5. But this is a local error. If we compute this error at each step, these errors summarized, error on the first interval plus error on the second interval plus error on the third interval, and so on and so on and so on. And finally, we will have the global error, the h power 4. It's also a very, very good result. The global error of h of order 4 means that if we decrease the step 10 times, the error will be decreased 10,000 times. We will check it now in Visual Studio. But before it, let me show you graphical interpretation. Suppose that we select an interval from a to b. Now a equals to x0, x1 is their middle point, x2 equals to b. The Lagrange interpolating polynomial that passed through these 3 points is a quadratic polynomial. Suppose it can be like this. And this is a graph of unknown function f of x. And in this case, we approximate area under the curve with the area under this quadratic polynomial. That's why the Simpson's rule, sometimes called parabola rule. And the error of this rule will be significantly smaller than the error of a trapezoid rule. Let's check it in Visual Studio. So this is the result for the trapezoid rule. Let me comment this loop. And now let's write a loop for the Simpson rule. What we should change for the Simpson rule? According to the formula, the formula for one interval should include f of x0 plus 4 f of x1 plus f of x2, and the common multiplication term is h over 3. What we should do? We should add here f of x1, f of xi plus 4 times f of x plus h plus f of x2, f of xi plus 2h. And pay attention that we should move the point xi not at one step h, but at 2 steps. H plus h. The second value will be not x0 plus h, but x0 plus 2h, this and this. And after that, we should multiply. We should multiply it on h over 3. H over 3. So from the first point of view, this formula is not very complex. Let's check the error of our computations. Let's run for number of intervals equals to 10, or I made a mistake. I have a very large error. It means that somewhere I made a mistake. Let's check it here. Where is the mistake? Xi plus 4 plus 4 f of xi plus h and plus f of xi plus 2h, and we move xi plus 2h and times h over 3. It's very strange, but it seems correct. Why we have this wrong result? Let me think for a minute. Well, it works, but now it's not. I know I know where the mistake is. The mistake is here in my presentation on this slide. As I remember, it should be minus here. Not okay, not minus, b minus a over 6. I don't know why it's not working, because it should works. Okay, let me modify this formula. Let me modify it like this. Here plus h plus h and h over 6. Yeah. Now it's correct. Now it's correct. But what happens in previous case? Or I understand what happens. I understand what happens. We consider different intervals. Well, okay, let me explain it. When we apply the Simpson rule, we should select the step 2 times smaller in comparison with the trapezoid rule. If we select the h as a difference between b and a, difference between these 2 points, and this distance equals to h. In Simpson rule, the h is the distance between these 2 points, and h should be 2 times smaller. So in our example, I should use h over 2. H over 2, and I'll get this result. When I select 10 points, the error has order 10 power minus 8. If I select 100 points, the order becomes 10,000 times smaller. Very powerful, very high rate of convergence. So this is a trapezoid rule. Let me write it here. And this is the Simpson's rule. Now let's consider the final rule of integration. So-called middle point rule. Let me remind you the main idea. We replace the initial function of the some interpolating function that can be easy to integrate. And the most simple function that we can integrate is a constant function, polynomial of degree 0. Let's replace the function of a polynomial of degree 0, a constant function, that passes through the middle point of the interval. In this case, the area under the curve of the function can be approximated of the area by the area of this rectangle. And the sum of the areas of the rectangles will be their value, the approximated value of an integral. If we consider one interval from x0 to x1, the area of a rectangle can be computed very, very simple. It's just it's a multiplication of the length of two sides of rectangle. One side equals to h and another side equals to the function value at their middle point, x0 plus h over 2. The order of the error will be 2. The error has order 2, h power 2. Let's check it. Let's implement the middle point rule. This is a Simpson rule, this is the trapezoid rule. Let me write the middle point rule. Middle point rule. According to this rule, we should compute the sum of the function at the middle points. If the step is h and the current point is xi, then the middle point will be xi plus h over 2. Then we should move the point xi and finally multiply the value of the sum times h, because h is a common term, common coefficient of these terms. Let's check this third formula. If the number of intervals is 10, the error will be minus 3 times 10 power minus 4. If we select the number of intervals equals to 100, the error will be minus 3.5, 10 power minus 6. We increase the number of intervals 10 times, and the error decreases 100 times, quadratic rate of convergence. If we increase the number of intervals to 1000, the error becomes of order 10 power minus 8, according to quadratic rate of convergence. Well, you see these two rules. Sorry, not two, three rules. Middle point rule, rule, and trapezoid rule. To understand in details how it works, I ask you to apply these rules for the following functions. Let's select the just one function, the exercise 1 under the letter A. Very simple function, x power 4, the integral from 0.5 to 1. I ask you to compute the value of this integral using these three rules: trapezoid rule, middle point rule, and Simpson's rule. I ask you to do it using pen and paper, compute it on a paper, to understand how these rules of integration works. This is a home task. The topic of the next lesson will be cover fitting. We consider how we can approximate the unknown function using a polynomial, but we will use not interpolating polynomial, but so-called least squares polynomial. And we consider how to approximate the unknown function using these ideas of least squares. It will be the topic of the next lesson. Well, today our lesson is finished. I stop sharing my screen. I stop recording.